Hi, welcome to Geography 4010 Applied GIS. This is a continuation of the skills that you learn in Geography 3435 or Geography 2020. Title of this presentation for our first week is Using Maps in GIS to Make Informed Decisions. We talked about previously what GIS actually is. GIS is the system. It's a combination of tools, techniques, software, things that you can hold, and the intangible that go into facilitating data-driven decision making. GIS isn't a GPS. It utilizes parts of GIS. It's not one particular software package, and it's not a static map, either printed out or something that you may see on your phone or tablet or whatever. And so it includes hardware, software, data, personnel, techniques, so that we can manipulate, analyze, and present information tied to spatial location with an end goal of facilitating data-driven decision making. We talked about previously the various components of a GIS. We've got people, software, hardware, procedures, which are increasing, that we cover in geospatial statistics, and some we'll cover in this class, as well as data. Hardware and software cost very little. The people and the data are the most expensive component of any GIS, and then a little bit is on the procedures. What do we do to GIS? We talk about queries, but we're always kind of pushing the frontiers and the limits on some of the different types of techniques that we can cover that can be performed on spatial data. But the most pertinent questions we address are, when we make a map or do any project, where are we going to get the data from? Who's going to perform it? Who's going to perform on it? And what are we going to do on it? And so these are just a major cost of any GIS enterprise, is having skilled professionals in order to do this. We can see an example here. Our typical desktop computer, which can run our software, anywhere from $800 to $2,000. Our actual software can be free, up to a few $1,000s. And then we have analysts. You can see some analysts over here on the right. These are former NCCU students who now work out in the field. They probably start $50,000 to $60,000 a year and work their way up from there. GIS has a number of related technologies: database management systems, computer-aided design, GPS, remote sensing, desktop mapping systems, World Wide Web. That's especially important as we try to share our maps on phones and tablets wirelessly. Statistical analysis systems. And so GIS pulls from those where there's a spatial component attached to these. When we talk about GIS, it's Geographic Information Systems. So I want to step back for a second and talk about, what does geography mean to us? A lot of times when we think of geography, it's memorizing countries and capitals. It's a lot different these days. Learning about different places in the world. And for the most part, memorizing countries and capitals and learning about different places in the world is very qualitative in nature. We do offer classes in qualitative geography, which are descriptive. Geography means Earth description, how to describe the Earth. Making maps. All right, that's getting a little closer to GIS. Even though maps are helpful, we use maps to display spatial information. They're not the only thing. We can do GIS and spatial analysis. We can analyze geographic data and make decisions about it with an end goal of facilitating data-informed decisions. Where are we going to build the next Lowe's or Walmart? What parcels do we need to buy in order to build that extension on the highway? How much money is going to be allocated toward that? And so the most important thing is data. Location data. Does data even exist? When we talk about projects, food deserts, placement of buildings, Where do we get the data? Do we need to create this from scratch? Like, creating data from scratch is the most expensive part of any GIS enterprise. And we do this on a regular basis. You may need to at some point in time in one of your projects or you work out in the field. What's your source of data? Is it census, state websites? Do we download it? How do we convert it to spatial format? And then the scale of data. Is it global data? Is it local data? Are there privacy considerations? And me personally, this is my skill set within GIS. What are the data standards so we can make high quality data that go into data analysis? So this analysis is high quality as well. But what's the scale of the data? And then eventually, how do we want to present those data? Words, charts, graphs, tables, photos, whatever we want to do. And so you can see scatter plots here. We're mapping income versus distance to a convenience store. So when we use the word distance or around or near, there's a geospatial component with those that do not exist in tabular data, that cannot be performed with tabular data. And this is where GIS comes in. Here we're looking at food swamps, rural food swamps. And so we can look at different counties and the percentage of people, but these are all ways that we can display data. Or something like this, some effective bar charts here. Now, what we've covered in GIS thus far are the different types of GIS data. We have vector GIS, where we represent geographic phenomena using points, lines, and polygons. And you can see here I've got major cities represented as points, I've got counties represented as polygons, and I've got smaller zip codes represented even smaller polygons, about 800 of these in the state. We have raster GIS, and in Geography 4010 we're going to cover a lot more of raster data, in which data are represented using cells. Now, we work with raster data on a regular basis. You take a picture with your phone, it's just composed of tiny little squares or what we call pixels. And then we have tables, non-spatial, CSV files, Excel, DBF files that have county growth or crimes, just big lists of data. And what we try to do in GIS is turn those into spatial format using some type of spatial identifier. Does it have a latitude and longitude? Does it have an address? Does it have a zip code? Does it have a county? If so, it can be mapped using some of the techniques that we covered in 3435, and we'll revisit here in a couple minutes. And so you can see here in our ArcGIS Pro software, you can see our table of contents where we have what we call standalone tables. And then we have feature classes or layers or shapefiles that are attached to attribute tables. And we'll look at those here in a little bit. When we model the world, we model points, lines, and polygons. So points could be represented as airports or wells or crime locations or tornadoes. Even though a crime might occur in a house, which is represented as a polygon, when we look at it as a city scale, we're not going to notice that little polygon. Same thing with lines, roads. Roads might have width, but if you're doing survey for your block, well, you might want to represent those roads using a polygon. For what we do at the county level, GIS level, lines are good enough. And then we have polygons like buildings, lakes, high-scale cities, block groups, counties, states. And they have area and they have perimeter. Lines have length, which are one-dimensional, and points are dimensionless, meaning all they have is latitude and longitude or location. The raster data model, you can see it's a mosaic of thousands of tiny pixels that represent a 2D array of equally spaced cells. We've heard the term pixel before. That represents, or that stands for picture element. And it's typically used to model continuous data. Things, and we're looking in this example here of elevation, temperature, air pressure. When we look at raster data, we're usually typically representing discrete data. I go from one county to another county, and it's typically nominal data. Here we're looking at quantitative data of elevation. And so we move over a little bit, we have a new elevation. Now there's always going to be this reconciliation between, well, how big are our pixels versus what type of phenomena we storing. You know, we have data called LiDAR data. We might get to 1 foot elevation data. Do we really need 1 foot elevation data? Is 10 meters good enough? Is 100 meters elevation good enough? Probably not. But when we look at something like temperature, do we need 1 foot, 1 foot resolution for temperature? No, maybe 1 mile. And so it's dependent upon the phenomena. But we see the raster data model here. This is a satellite image here of RDU Airport. And you can see it all zoomed out. It looks nice. But when we zoom in, we can start to see the pixelation of it. Now, how are data stored? Okay, we focused on that a lot. Now, in our ArcGIS profile, we looked at APRX files. In our previous incarnations of GIS software, they were called MXD files. They store the maps, the symbology, the layouts, the graphs, any connections that we have. And then we have a GDB. That actually stores the individual points, lines, polygons, vertices, nodes, the attribute data that connects those. And then we have other types of GIS data, personal geodatabases, shape files, TINs, other things as well here. But this is an example here. When I look at Windows Explorer for my exercise, you can say exercise 1 is really small, but when I look at the points, lines, and polygons for the GDB file, it's about 20 meg. It's much, much bigger. Okay, much larger. So this is where we're storing the individual points, lines, and polygons, and it depends upon the type of data you're working with, and how many features you're working with, and how robust the data are. These files can get really big really quickly. And then when we look at these databases within the confines of ArcGIS Pro, this is exactly what they look like here. So I can see this is a point, this is a polygon, this is a point. These are standalone tables right here. We also talked about data and field types. Data can take on different forms based on what we want to store and how we want to store it. I alluded to the idea of nominal data before for counties. I go from one county to the next county. Well, it's just nominal data. Nominal data. The names of things. We have ordinal data, which is typically order, like 1, 2, 3, 4, your grades. And then we have numerical data, and different types include ratio data and interval data. Interval data might go below 0. Ratio data might start at 0. Things like population. We can't have negative population. So something that has a population of 10,000 is twice the population of something that's 5,000 that you can't really do with interval data. I can't say it's 100 degrees out today, it's 50 degrees out yesterday. I can't say it's twice as warm because we can go well below 0. And with that, we have our different field types like text, dates, long, shorts. Long and shorts refer to integers, numbers that do not require decimal points. Long numbers go from about negative 32,000 to 32,000. 32,000. Shorts go from negative 32,000 up to about 32,000. Longs can go really long. Then we have floats and doubles, which are numbers that require decimal points. So something like Pop 2010 doesn't require a decimal point, so we can store that using a long because we know that most cities, counties, states are going to go above 32,000. And so with these field types, that just addresses the amount of memory and space that's required to store each of these. In a day and age where we walk around with, 64 gig, flash drives or whatever, this memory isn't necessarily an issue. And so when we look at this in ArcGIS Pro, you can see examples here. I have ID. This is left justified. So these are zip codes. And so it's left justified. So this treats it as a text. This is probably a long, but poverty rate and percent minority. These are floats or doubles. Floats just store really smaller decimal numbers. Doubles store really large ones. Me, when I work with integers, I store everything as a long. With floats or doubles, I store everything as a double. So I do not lose any what we call precision. Other things that we talked about previously are creating maps using layouts. Most of the maps that we look at these days are going to be on phones, computers, tablets, or whatever else. But we can use ArcGIS Pro to create something called a layout. So this thing can be exported to a TIFF. I store everything as a TIFF or a PDF, so it can be inserted into a PowerPoint. We talked about rules on symbology, coloring, placement of objects, visual hierarchy. Where do we want to put things? Where do we want to put elements? What's the most important element? What types of colors can we use? We talked about the purples and the greens as opposed to the reds and the oranges and the white to black, or the gray to black. So make sure you understand about what entails a high quality map, because when you write a paper, you're going to insert these. Now, a lot of the maps these days, we can click a little button up at the top that says share, and we can just share this to the internet. And we'll cover that at the end of this class. Working with tables and turning tabular data into GIS. This is one of my big skill sets, where that I find some neat data on population increases or income or whatever from the census, and how do we turn that into spatial data that we can display. Now, some things we can do, we can calculate and create new columns from existing columns. So we can derive data like population increase, sex ratio, the number of males per female, 100 females. But we can also turn tabular data into a join function. We can create data using addxy. In this class, we're going to talk about geocoding and then summarizing data to count the number of times an element appears. So I can download data, and you can see this example right here where I'm looking at North Carolina counties, population increase, and I can join these. I see a column here called county, column here called name. I can just add this to the end of my attribute table. I have an attribute table right here that's linked to my individual points, lines, and polygons. And then I can add this column to the end and derive certain information from it as well. And so with that, we talked about non-spatial data. Tables have no spatial data attached to them, can be sorted, brought into GIS and mapped as long as we have spatial location attached to those. So we can download lots and lots of data from the census, FactFinder 2, which is now migrated to something called SEDSI, Department for Health Statistics, Department of Public Safety. There's tons of data out there. And if you happen to look in our modules down at the bottom, I have tons of data sources out there. And so all you need in order for something to be mapped, a FIPS code, Federal Information Processing Standard, a county name, latitude, longitude, northing, easting, so that we can map data. So we can download a table like this. We're looking at age-adjusted cancer mortality rates in North Carolina and map all of these. So we can map these. Now, we're not going to know, when we look at Alamance County, we're not going to know where there's 141 deaths occurred, but we can compare these rates to Alexander and Ashe and Beaufort and look at clusters of colon rectum cancer for these particular counties versus other counties. We can look at rates right here, and these are, I think this is COVID rates that I downloaded at one point in time at the zip code scale. And so we can make high quality maps like this. We talked a little bit about finding relationships between two different variables. So we were looking at EOG scores versus attendance. And so I can graph these. And so you can see my percent daily attendance, and you can see here the x-axis is attendance. The y-axis is students who scored 1 or 2 on EOGs, mean non-passing. And you can see as attendance increases, the failure rates decrease, except for this one over here. So we can map these. And if you take geospatial statistics, we're going to do a lot more with these. And then we can also create or derive fields from existing fields and calculated from existing data. So we can create something or calculate something called sex ratio, which is the number of males for every 100 females, and map these. And so you can see some of the really interesting things that we can derive. We can look at alcohol-related fatalities. This is a student who now works for the NCDOT, what they've done. Now, if I were to see this map in the upper left, it really means nothing to me because California, Texas, and Florida probably have a lot of DUI fatalities because there are a lot of people who live there who could potentially be in DUI crashes. But now, in map 2, we can look at the percentage of highway fatalities related to DUI. And so you can see these ones in blue right here, up to 44 to 50% are related to alcohol. And then we can look at the percentage or the rates of people who die of DUI fatalities. And you can see here in Wyoming, it's actually right here 1.5 times more than any other state, which I think second was Montana. And so we can look at some of the reasons for these and how to remediate these. We can add XY data. So if we have latitude and longitude, we can bring it in using something called the geographic coordinate system. They represent any coordinate system, latitude and longitude, and we work with the World Geodetic Survey, but there's other geodetic surveys out there that are a little bit older. We can summarize data, so we can count the number of times something appears. So this is crime data, so that we can show, how many weapons violations or how many crimes occurred on a particular day so that we can sort this. Now, this is going to be a standalone table because obviously you can't see anything related to location. But this just gives us extra insights from these. And then we can query data. And so we can ask questions of the tabular data that compose each feature class. We can do a location query, which you cannot do in Excel and filters and anything else related to tabular data management. So we can ask locations about geometrical relationships between feature classes. I want to find all of the crimes within a certain distance of an area. And if you were to look at the attribute tables attached to those, you will not see those. And so now we can see zip codes. I want to find all the COVID rates greater than 1,000. COVID rates greater than 1,000. And previous versions of GIS software, we generated these things called SQL statements. Now we have a query generator that allows us to auto-generate SQL statements. Now I'm looking at, let me find all the zip codes within a certain distance of a city so I can make some assumptions or make some statements, hypotheses. The COVID rates within close to cities are higher than areas further away. And so you can see we're looking at all the zip codes within 20 miles of a major city. And so we have zip codes within a distance of city, and I specify my search distance. So we have these really powerful editors and GUI generators right here, or GUIs that generate these queries. And GUIs just stands for Graphic User Interface. Now, we have a lot of things that we can click on here, but keep in mind, the more that we can possibly click, the more that we can possibly mess up. We can run a spatial join, count the number of features within a particular polygon, because you can see up at the top, I've got tons and tons of crimes right here, but I just want to count the number of crimes and then normalize by population using some of the techniques that we've talked about already. Looking at all these points right here is very exhaustive. So now I can group these by zip code or census tract or block group or whatever I want. Normalize by population and look at associations between socioeconomics and race and access to transportation or whatever that we can derive at that scale. And so we can make powerful maps once again. So this is a great example of a spatial join. This is from a previous student who wanted to count the number of hospitals within a particular by county in South Carolina and then normalize these. So we can look at the number of hospitals right here. So instead of looking at a map right here where all the hospitals are, which are powerful, now we can map South Carolina and its counties, the number of hospitals and the number of hospitals per person, in this case per 10,000 people. And then we started talking about geoprocessing applications. So things like buffers, clips, unions, intersections, nears, and they satisfy our ands and our or queries. So something like an intersection, I want to find all areas within 5 miles of this and 10 miles of this, and it only gives me those. or that a union within 5 miles of this or 10 miles of this. So we satisfy the and the or that and satisfies one, or and satisfies both, or satisfies one or the other. So you can see examples of unions. You can see examples of intersections. And then working with census data. Census is one of the great sources of data. We can download these data at various scales. And so we can look at phenomena such as adults age 25 plus without a high school diploma. This is one of our former students. This is what they do for a living. So we can map parcels and look at the sales deed dates for these. Now, some of the things that we plan on covering this semester: projections, managing vector data, managing raster data, cataloging data, editing data, downloading your own data, which to me is important. And as we evolve to creating your own data and connecting to services and some more of the geoprocessing. So we can look at buffers. These are buffers right here. So we're looking at all tornadoes within a certain distance here on military bases. These are buffers on campus. These are distances, buffers around Wi-Fi transmitters on the NCCU campus with 100 feet buffers, less than 100, 100 to 200, 200 to 300. Here we're looking at raster data. So we've extracted data to look at North Carolina air quality data. We can look at convenience store accessibility. So the proximity of analysis, scatter plots, okay? Now, lines of best fits, what we talk about in geostatistics, and then overlays like we talked about before that are common. And you can see we made buffers around parking lots. We made buffers around Wi-Fi transmitters. And so this area in thatched red are areas that satisfy both of them. And then we'll also get into geocoding, because we do this all the time with our phones, where that we map data by addresses. But you can say, who wants to do this 5,016 times? We can do this using services. These are relatively easy to do. We can make drive sheds right here. So instead of making buffers, which are good, but these drive sheds are a little bit more practical, especially when we talk about driving. So you can see these areas in pink right here are 45 to 50-minute drive, and you can see it extends further and further along the interstates where you can drive faster and cover more distance in the same amount of time as your local roads. Other things we'll talk about are metadata. It'll tell projection information and information about content creator, contact information, everything for that as well. We see these all the time. We have a picture here, and you can see up at the top, it gives us very basic metadata about it. And you can see why, collected location right here. So even when you take a picture, it's got metadata about it, believe it or not. And then by the end of this class, what we'll try to do is cover some skills to help get you ready to be successful in the GIS workforce. GIS, earth sciences are growing fields, okay? GIS is a powerful technical skill that can set you apart from other applicants in the job application process. And so to be successful in GIS, you've got to interest the principles of geography, computers, math. You don't have to be great at math, but understand calculations, percentages, conversions of units. Because, the biggest thing when we start evolving and moving from the classroom to the workforce is focusing on problem-solving skills, working with others, writing and public speaking, and we do this through internships and these bigger projects here. And that's our ultimate goal. Our ultimate goal is to get students ready for the workforce. And we do this through internships and projects and all that other good stuff. So that's the conclusion of our intro. We'll post more of these as well. And stay tuned for the next lecture.